Hello students and fellow teachers. This is the first recorded video lecture for Theory and Pedagogy of Single Variable Calculus. Tentatively I put in Math 5110 as a course number, but don't pay too much attention to that because it can change later. The permanent course numbering did not come out yet. Speaking of permanence, by the way, nothing is at this moment. Everything is tentative, this entire project I mean, and consequently everything is subject to change, the course number, the course title, even the curriculum. Of course, I'm making my case to establish this as a permanent course, and hopefully it sticks. Alright, let's begin. This is the first lecture on the first week, so we have to begin with some review. And of course, it's going to be impossible to review everything in precalculus in a single week. So what do? We select some miscellaneous topics here and there, and we're going to cover those. We begin with inequalities, roughly following the order of our textbook, the main textbook, a first course in calculus by Serge Lang. In that book, our textbook author did something peculiar. Instead of starting from the properties of inequalities as an axiom, and defining the set of positive numbers as the set of all real numbers that are strictly greater than 0, he does the opposite. He decided to establish the concept of positivity as an axiom and derives all the properties of inequalities from positivity. Kind of strange, kind of going backwards compared with our common sense, but it works out just fine. Okay, let's respect our textbook author's decision, and here we go. There exists a certain non-empty subset P of the set of all real numbers R with the following properties. Number 1, trichotomy. For any real number A, one and only one of the following holds. A is 0, or A belongs to P, or negative A belongs to P. Here, negative A means the additive inverse of A. In short, A is 0, or A is positive, or A is negative. The second property, the set of positive numbers P is closed under addition and multiplication. That is, for any pair of positive numbers A and B, A plus B and A times B are both positive. With these properties of positivity, it is possible to derive these properties if we define the inequality as this. Define A is less than B as B minus A is positive. Yes, we established the positivity, so we can define the inequality like that. And once you do, it is possible to prove these, even though I'm not going to do it this time. Maybe a couple of weeks later, but not just yet. This is the first week, so I don't want to go too deeply into these kind of things, not just yet. First, the trichotomy. For any pair of real numbers A and B, one and only one of the following holds. A is less than B, or A is equal to B, or A is greater than B. By the way, this trichotomy is a little bit more general than this trichotomy, in a sense that if you put B equals to 0, then this one corresponds to A is less than 0, which is this one, and A is equal to 0 right here, and then A is greater than 0, this one, if you put B equals to 0, that is. But amazing thing is the opposite direction also holds. That's going to be trickier because this one is a little bit more general and this one is specific. So proving specific from general is pretty much straightforward. Just plug in B equals to 0, the specific quantity, and everything just follows. But going the other way around is actually harder, but it can be proven. It's not super hard, so if you're familiar with proof writing, actually you can do it. But at this moment, let's just take it for granted and let us just move into the second property here. This is called the transitivity. A is less than B and B is less than C, then A is less than C. And then there are two more. The inequality preserves addition. If A is less than B, then A plus C is less than B plus C for any real number C. How about multiplication? Does inequality preserve all multiplication? Actually no, but it does preserve the multiplication by a positive number. If A is less than B and C is positive, then AC is less than BC. What if C is negative? Well, in that case, you have to do something like this. When C is negative, negative C is positive, so you can multiply both sides by a certain positive number, which is negative C in the case, and then do some algebraic manipulation. We end up with negative AC is less than negative BC, and add AC to both sides, we get that. Add BC to both sides, and finally we get that. So we have the common notion. If you multiply by a negative number, then you have to flip the direction of the inequality. The standard properties 1, 2, 3, 4, yes, we can prove those, but I don't want to go too deeply into that at this moment. So let's postpone those foundation, those strict proofs, the rigorous proofs. Let's just move on to some easier examples. Okay, here we go. One example is here. According to our textbook, this example appears in, let me see, page 7. In page 7, actually, our textbook is asking you to prove only one direction. When A over C is less than B over D, then AD is less than BC, only that. However, we can do a little bit better, and we can actually prove the necessary and sufficiency. Okay, let's prove the forward direction. This is the same as our textbook's forward direction. Let's suppose A over C is less than B over D, and we're going to use a certain property of inequality, especially we're going to multiply a certain positive number. So what positive number can we multiply? C times D, because C and D are both positive, and set a positive number is close on the multiplication as we see over here. So C times D is positive. So if we multiply by C times D, this is what we get. A over C times CD is less than B over D times CD. And after cancellation, what do you get? AD is less than BC. That's precisely what we wanted. And that example appears in our textbook in page 7. How about the other direction? Well, that's a little bit trickier. Well, we have to start from here. AD is less than BC, and we have to multiply by a certain positive number. And what will that be? It'll turn out if you multiply 1 over CD, everything works fine. That's positive and that's positive. So if you simplify D and D in the left hand side, C and C in the right hand side, we get what we want, this one. But there's a bit of a problem. How do you know 1 over CD is positive? Well, it is true, but you have to prove it. Well, C times D, the denominator, is positive, yes, because the set of positive numbers is close under multiplication. It appears as one of the axiom. But what about the reciprocal? Does it mean, let's see, if x is positive, then is its reciprocal 1 over x also positive? Is this true? Yes, it is, of course, but you have to prove it. If you prove it, then everything here is valid. If you do not prove it, then there's a bit of a gap. Well, how do you prove that? I'll leave that to you. It's a bit of a challenge, but not super hard. Okay, let's go over to the next notion, the square root. And our textbook author decided to approach like this. For any non-negative real number a, there exists a certain real number b such that b squared is equal to a. Is it true? Wow, there's a big question. Is it really true? The answer, of course, is yes, but the big question is how do you prove it? It turns out that this proof is very, very hard, and I don't know whether we will come back and prove this sometime this semester or if I have to dump it over to some other course, but it is necessary steps, so we will have to prove it at some point. I think we'll have to use intermediate value theorem, but we're not ready to discuss it yet. For the time being, let us just take it for granted. Let's suppose that there is a certain real number b so that b squared is equal to a whenever a is non-negative. If a is negative, then of course such b doesn't exist, but when a is non-negative, let's suppose it exists. Alright, once we have the first line, the next line is easy to establish. B squared is equal to a. That's equivalent to negative b squared is equal to a, because negative 1 times negative 1 is positive 1. Consequently, one of them has to be non-negative. If b is non-negative, fine. If b is negative, then negative b is non-negative. So one of them is non-negative, and we're going to define square root of a as one of those non-negative stuff. So if b is non-negative, then square root of a is b. If b is negative, then square root of a will be negative b, so that square root of a is always negative. By the way, this is a little bit vague, especially right here in the first line. Therefore, our textbook author did not use the term definition and define the square root. He just spends a couple of paragraphs in page 8 and just move on to the next one. And here in page, is it page 8 or is it in page 9? It's in page 8 of our textbook. And here our textbook author uses the term definition and precisely define the absolute value. He does it this way. Absolute value of a is square root of a squared. It's rather peculiar because almost all elementary algebra textbook defines the absolute value of a like this. Absolute value of a is equal to a if a is non-negative. If it is negative, then we take negative a to make it positive. But our textbook author decided to do it this way. Why? Well, I can only speculate because I haven't had any private discussion with the textbook author. But if I take a guess, it may be this because if you expand this idea to complex numbers, then we can define the absolute value of complex numbers like this. This is a standard definition of the absolute value of the complex number, a plus bi. And what is a real number? Well, special case when b is equal to 0, so that imaginary part doesn't exist. So if I plug in b equals to 0, this part drops out and we have just this one. So this definition of our textbook author can be extended naturally toward complex numbers and actually even further to vectors and so on. But this definition doesn't work that way. I think that's why our textbook author decided to define the absolute value like this rather than that. But it's okay, we can prove one from the other. How do we do that? Pretty trivial. Case 1, if a is non-negative, then a squared is of course a squared and itself is non-negative, so square root of a squared is a because a is already positive. Trivial. The next is not that trivial. If a is negative, then negative a is positive, so that will be the square root because we want square root to be non-negative. And that's how we can prove it. Just trivial observation. Now we have two more, and looks like we'd better cover this 1.7, this property, which appears in page 9 of our textbook, theorem 2.2, excuse me, and the triangle inequality that appears in page 9 as well, theorem 2.3. These two and some examples in the next video. So wait it up to here, and let's pause and then let's meet again in the next segment of the video.